Topic for today and the next lecture will be circuit complexity. So far we've been talking about Turing machines and algorithms to decide languages. But now let's talk about a model of circuits to decide languages. So what is a circuit? Well, it's exactly what you would think it is. It's got, AND gates, OR gates, and NOT gates. And each of these gates would take two inputs each. This would just take a single input, and they give outputs. Now the key difference, the way that you may normally think of circuits, and typically when you think of circuits, you're thinking of a tree, which is a formula, is that the output can be split into two parts, and we'll see that this is a big difference. Okay, so the idea is that your circuit is actually a DAG. So I'll say a circuit is a DAG because you think of sort of the inputs flowing into the gate, the outputs are flowing out, where leaves, or you can call them sources, are labeled, we'll say x1 to xn, or 0, 1. So these are the inputs. Internal nodes are labeled, or, and, or not. And each gate has out degree, has both in degree and out degree, at most 2. So what's key is that it's at most 2, right? And if the out degree is always 1, then the circuit is a tree, and this is just called a formula. This is called a formula, which is different from a circuit. Okay, so just to give you an example of a simple circuit, so the idea is you can reuse a computation in a circuit. So let me give you an example. So let's say suppose we're looking at the function, which was going to have just 3 inputs, or 4 inputs in this case, and it's x1 or x2 or x3 and x1 or x2 or x4, let's say not. So note that what I have written here is actually, it's a CNF, it's a formula. You can write this as a tree, as a circuit that has a tree. But observe that this x1 or x2 is used in both clauses. So in a circuit, I can compute this once and then reuse the value. So the way you would do that is you would say, here's x1, x2. This I can take another OR with x3 over here, and I'll take another OR with a NOT gate with x4, and then so you could imagine directing it, all of these upwards, and then that is the output. Right, so it allows us to reuse this x1 or x2. If you had to make this a tree, then there would be 2 copies of that gate. So circuits are smaller than, or can be smaller than formulas. Now you might say, why is the out degree 2? Why isn't it larger? And so I'll just tell you why. So first let me say the size of a circuit, the size of a circuit is the number of vertices plus edges in the DAG, the corresponding DAG. Right, so the size of the circuit, and it depends. In some places they only count the edges, in some places they count both the edges and vertices. It really doesn't matter. I mean, for our purposes, up to a constant fraction, it doesn't matter. Now, because each gate has an out degree of at most 2 in our setting, the size is really just O of the number of vertices, which is really O of the number of gates. Now you might wonder, you might say, well, I mean, out degree of 2, I mean, you could have an out degree which is much more than 2. It doesn't seem to make much of a difference. And if you think about it, by increasing the out degree, you do increase the size because you count the number of edges. And what you can observe is, and that is often, this is called the fan out. The degrees are often called fan in and fan out. So let's just say you had multiple things. You can replace this essentially with a tree-like structure, right? So if you say that there's only 2 outputs, what you can do is you can imagine just sort of so let's also, for convenience, just to sort of write this out, we can create a no-op gate. And this does nothing, right? So this just sort of pipes x1 to x1. And you can simulate a no-op gate by doing 2 negations in a row, right? So it doesn't matter. So what you could do is you could start from here, you create this, and then you could create a negation, and then fan that out twice, and a negation, and that goes fan out twice. So now one input has been split into 4, and we could split that into 8, so on and so forth. So essentially what you do here is a no-op. Right? That's a no-op. And so what this means is you can always simulate every circuit with large fan out by having fan out at most 2 with just a constant increase in the size. And for that reason, we just focus on the out degree being 2, and that's convenient because then in our setting the size is just O of the number of gates. Okay, so all we've done is, in some sense, we've basically converted this, we've converted large fan out into a binary tree. That sort of copies the value. It copies a value. Okay, so is this clear? Does the notion of a circuit make sense? Any questions? Right? So we're going to start by understanding what circuit complexities are going to look like. We'll start from some classic theorems of Shannon, and then we will connect this back to Turing machines and time complexity. Right now it seems like we're going off on a different topic, and we'll bring it back to actually the most fundamental question of P versus NP and how P versus NP relates to circuit complexity. So I'm going to start by a classic theorem of Shannon. This was proven in 49. And so there are really 2 parts to it. It says for every n, and maybe I should just to be clear, I'll say a circuit C of n on n inputs, computes a function f 0, 1 to the n to 0, 1. And so we'll just think of the output in this case as just being a single bit. A circuit computes a function if, for all x of length n, Cn evaluated on x is the same as f evaluated on x. Right? This is just saying the obvious thing, that the circuit computes the function. And that's what it means for a circuit to compute a function. And again, I mean a circuit that has a single output, that outputs a single bit. And in general, we can think of a circuit computing a more complex function where there are multiple outputs and it's all exactly the same. There is no difference. So Shannon said that for every n, there exists a function f sub n that requires a circuit of size omega 2 to the n over n to compute it. Moreover, for all functions f going from 0, 1, for all n-bit functions, f can be computed by a circuit of size O of 2 to the n divided by n. So what this says, and this is a classic result of Shannon, this was improved by Lyapunov. Lyapunov, and I think this maybe in the 50s or the 60s, actually showed that the constant there is 1. Like, you can nail it down to exactly 2 to the n divided by n, and you can compute it by a circuit of essentially 1 plus little o of 1 of 2 to the n divided by n. Okay, so this is a non-trivial improvement because you'll see that getting a circuit size of 2 to the n is actually quite easy, but 2 to the n divided by n requires some cleverness. All right, any questions about what this theorem means? Like, what is the theorem statement? Right? Let's look at the proof. So I'm going to begin by proving the first part. Okay, so I'll prove the first part here. Let's start by asking, and it's a classic counting argument. How many functions on n-bit inputs that provide a single bit output exist? How many functions exist which have n inputs and 1 output? Any guesses? How many functions exist?
Is it 2 to the n?
Why 2 to the n?
Because, the function is of length, or the function input is of the number of functions. The input is of, I would say, okay.
Right.
I've changed my answer. Countably infinite.
No, it's finite. It's just n bits. The input are n bits and the output is 1 bit.
Oh, well, couldn't you... Oh, okay, right. Going back to my original answer, I would say for every bit, there's 2 choices.
For every output, there's 2 choices.
Right.
And so how much is that? Right, that's a question. How many functions exist? Okay, let's see. What is your function? Your function is the truth table. Write it out as a truth table. Okay? So here are all inputs. So this is of length n. These are all inputs. And so for each, there's either a 0 or a 1 or 1, 0, whatever, right? There's all of this. Okay, so how many entries in the truth table? How many entries in the truth table?
That was n times n, like individual entries.
How many possible inputs are there for such a function?
N. Right.
Okay, so my badly phrased. My question is, there are n inputs. So think of, what you have is f of x being either 0 or 1. How many x's? How many possible x's? This is badly phrased on my part. I mean, input is sort of overloaded here. There are 2 to the n possible settings of the input. Right? There are 2 to the n strings of length n. That's how many inputs there possibly are. For each input, the output has 2 choices. So the number is actually 2 to the 2 to the n.
Oh, right.
Right? It's 2 to the 2 to the n. So it's doubly exponential in n. Now what we'll do is, so that's counting how many functions exist. Let us count the number of circuits of size so what I'm going to do now, and this is going to make things just easier for us with respect to the calculation, is because if you define the circuit to be the number of vertices plus edges, you basically get it's O of the number of gates. Let's actually say it's the number of vertices, so that the size is exactly the number of gates. Okay? So the size is exactly the number of gates. And this is just going to make our calculation easier. It works whichever way you do it. So let's say the size is the number of gates. And because we have O's and omegas there, it doesn't matter. So let's just count the number of circuits of size S, meaning that it has S gates. So how do you represent a circuit? So let us represent the circuit by an adjacency list. So each and the leaves are numbered x1 to xn, 1 or 0. Right? The leaves are just numbered x1 to xn. And what we can also do is we can assume, and again, because we can essentially sort of do this no-op thing to spread things out, we can say that where leaves are labeled x1 to xn, and we'll also enforce that each xi appears in exactly one leaf. Right? So in our circuit, we're just going to enforce that there are exactly n plus 2 leaves. Okay, there are exactly n plus 2 leaves. So what does our circuit look like? It's some DAG.
No, wait, move up.
So I'm just gonna, yeah. So this is, some DAG that we have here. And in the end, we're just going to have these leaves numbered x1 to xn. There's the 0 leaf and the one leaf, and of course these are just going to be sending their values in. The leaves are numbered x1, xn to 0, so we can fix the numbering of the leaves. We represent the circuit by an adjacency list, and there are S gates. So the representation has to specify the gate at each vertex and the out neighbors of each gate. That's it, right? And the in neighbors get specified automatically through the out neighbors, because if you specify all the out neighbors, then you'll specify the in neighborhood as well, right? So you don't need to explicitly specify it, that's automatic. So the representation has to specify the gate at each vertex and the out numbers of each gate. And in the leaves, it has to specify the leaves need a label in x1 to xn 1 or 0. Okay, so we'll say the number of different circuits, the number of different circuits of size S is essentially, and we'll just say is at most, the number of ways of labeling the leaves times the number of ways of setting the out neighbors times the number of ways of setting the gates. Okay? Right, so it's the number of ways of labeling the leaves. It's the number of ways of selecting out neighbors. So we could imagine that these vertices are all labeled. They're all labeled like 1 to S. Okay, so now let me sort of write all of this down. So the number of ways of labeling the leaves, that's just n plus 2 factorial. It's n plus 2 factorial because there's there are n plus 2 possible values that I could set at the leaves. How many ways of setting the out neighbors? So each vertex is going to pick 2 out neighbors because that's the out degree. Okay, so each vertex picks 2 out neighbors, and so that's S choose 2 choices for each vertex to the power S, right? So S choose 2 is the number of choices to pick the 2 out neighbors, and that is powered. That is, you take it to the S of the power. Times the number of ways of setting the gates. Now, there are 3 possible settings for the gates, and or not. So that's 3 to the S. Right? It's 3 to the S. Now, note that you can assume that, in a sense, S is going to be at least n, because that's the number of vertices. So what you get is this is at most, and you can we'll just upper bound this. We'll just take a very crude upper bound of S to the 2S. It's a very crude upper bound times this is also S to the 2S. Again, very crude upper bound times 3 to the S. Right? So this I'm just going to write, taking logs and everything. I can just write this essentially as okay. So let me write it a bit carefully. I'll say this is 2 to the power is 2 to the power 4s log s, right, taking log base 2, plus, s log 3. Or am I doing this right? Yes, right? So the number of different circuits of size s is at most this quantity. All right. Any questions?
Yeah. Are self loops allowed for the out neighbors?
Self loops are not allowed. So I could probably sharpen this bound, but self loops are not allowed, right? Think of it as actually a circuit where the signal has to complete. So that's a good point. So it's a DAG, right? As I specified in the beginning, a circuit is a DAG.
Right.
Yeah.
So you probably could refine this a little bit, but I can see, just for the sake of simplicity, that I can see that this is accurate.
You can refine this a little bit, but what you're not going to beat is s to the s.
Sure.
Because every vertex has to choose 2 out neighbors.
Right.
And so essentially that boils down to saying that, well, okay, I mean, everybody has 2 choices, and then that has to, that's going to basically give you s to the s.
Gotcha.
All right. Okay. All right. So I'm just going to write that bound over here again. Remember, so it was 2 to the 4s log s plus s log 3, right? And again, I just want to, I want to make this easier to deal with, so that we don't have to sit around with all of these. And I will just say that, assuming that s is a sufficiently large constant, I can just write this as 5s log s, right? Assuming that if s is a sufficiently large constant, then I just get this. Okay. So now let's say suppose s is less than 2 to the n divided by c, we'll say, I'm sorry, not log, c times n. This is just going to be some constant. We can pick this constant appropriately. So it's just 2 to the n, s is less than 2 to the n divided by cn. Let's go ahead and plug this bound in. Plug this in. So 5s log s is going to be at most 5 times 2 to the n divided by c times n times, now we take log s. I'm just going to upper bound this by log, okay, so I'll just write this out, divided by cn. Now I'll just upper bound this by saying 5 times 2 to the n divided by c times n. I can just upper bound this by n. Just upper bound this by n. Right? So the n and n cancel out. And what I get over here is, assuming this constant was greater than 5, then this is at most 2 to the n. What this means is when I plug this bound in, this is strictly less than 2 to the 2 to the n. And remember, we said there are 2 to the 2 to the n functions of n-bit, n-bit variables. But if the size of the circuit is less than 2 to the n divided by 5 log n, 5n, I'm sorry. So the number of different, that is distinct, circuits of size at most 2 to the n divided by 5n is strictly smaller than 2 to the 2 to the n. Thus, there exists a function, and we'll call this f of n. This is the hard function on n bits, because we know that there are more functions than there are circuits. This is a counting argument. There exists a function that requires a circuit of size at least 2 to the n divided by 5n to compute it. Right? And this ends the first part of Shannon's theorem. Indeed, if you think about it, most functions, because if you just change the constant over there, you can show that this is going to be not just less than this, it's going to be less than 2 to the 2 to the n divided by 1,000. So it's going to be so much smaller. Most functions require a circuit of size 2 to the n divided by 5n to compute it. Right? So any questions? So this is in some sense saying that there are always functions that are going to be exponentially hard. By hard, I mean exponentially hard with respect to circuit size.
I'm a bit confused about how we were able to say that S is less than 2 to the n divided by C times n.
We're assuming that. So what we're saying is, so here's one way to think about it. Consider all circuits of size less than that. So there's a family of circuits, all of whose sizes are less than that. That family of circuits, the number of such circuits is at most strictly less than 2 to the 2 to the n. What that means is there must...
So, are we just arbitrarily choosing 2 to the n over n?
Yep.
Okay. Fair enough.
We just chose it. We just chose it to make the math work.
Okay.
But here's the remarkable part, right? Shannon also proves that for all functions, there's actually a circuit of size 2 to the n divided by n that computes it. So this seemingly arbitrary choice was the best possible choice.
Wow.
Right? So it seems like, this is, you just plugged in 2 to the n divided by n to make it work. You would think that the answer should be like 2 to the n. Like, why is it 2 to the n divided by n? It seems like funny.
Yeah.
Like, if I told you it was 2 to the n, you might say, like, that makes sense. There's a truth table with 2 to the n entries. For each entry, you need like a separate gate structure.
Yeah.
But it turns out you can beat that.
Oh, interesting. Yeah, I was thinking that exact same thing, actually. I was thinking, 2 to the n I would have expected, because, the entries of a truth table, but that is interesting.
So you can actually get a compression of a factor n, and, that's a pretty large factor when you think about it.
Yeah.
And so I'm going to show you how to do it. I'm going to sketch out the proof, and then working out the details is actually is part of the third homework problem. Okay, but any questions about this argument? And this is a classic, what's called a counting argument. You want to show, essentially, when you show that one set is larger than another set, then you get this element, basically, which shows the lower bound here. So all you need to do is to show that there are fewer functions on circuits of size 2 to the n divided by n. The number of distinct circuits of size less than 2 to the n divided by 5n is strictly smaller than 2 to the 2 to the n, which is the number of functions on n bits that output 1 bit. Okay, questions? All right. Now let's go to the second part. Now, the second part is actually is harder. So I'm going to start by a simpler claim, and this is something that is not very hard to prove. You wouldn't be surprised to see this. is that consider any function on n bits. There exists a circuit of size, and I'm just going to put some arbitrary constant to help me out here, 50 times 2 to the n, that computes f. This is not a very surprising bound. You might say, well, of course, you need to put this extra gate. You need to, for every entry of the truth table, you have a bunch of gates that sort of handle that entry. And indeed, the proof is by induction. So we can simply write out f of x1 to xn. It just says that if you set x1 to 0, then you're computing an n-1 bit function. If you set x1 to 1, then you're computing another n-1 bit input function. So I'll just write this out. This is not x1 or f of 1 x2 to xn and x1 or f of 0 x2 to xn. So in some sense, this is just saying that if x1 is equal to 1, then it's just f of 1 to xn, and if f of x1 is 0, then you just do f of x 0, where the first bit is set to 0. Right? So this is the basic construction here. Okay, and then we just do it by induction. So then we could say that, okay, so how do you compute f? Well, okay, so you have an AND gate here, then you have one OR gate here, one OR gate here, and then you have NOT of x1, and here you have x1. So you could just combine these leaves into one, right, by just adding an OOP gate, or just adding two NOT gates in a row. And here you have to put whatever circuit you want that computes f of 1, and here you put your circuit that does f of 0. Whatever. Does this make sense? So you get a recurrence, you get the size for computing the n-bit function is at most 2 times the size of computing an n-1 bit function, plus, we can count 1, 2, 3, 4, 5, 6. I'll just say plus, at most 10. So if you unroll this, and if you can prove this now by induction, you'll just get that this size of n is at most 10 times the summation of I going from 1 to n of 2 to the I. Right, then this you just prove by induction, and this will just give you, or whatever, this will give you like at most 50 times 2 to the n. And I might have been a little sloppy with the constants, but it doesn't matter. I'm just giving an upper bound here. So the size, this is simply just doing the obvious inductive mechanism and just unrolling it entirely. And you can prove this you just prove by induction. I encourage you to work it out exactly so that you're confident. For the sake of the homework, you can just assume this theorem. Just go ahead and assume this theorem. Okay, any questions about that?
Just to clarify, you're just taking this function and just computing the size, and then once you unravel it, then that will be the size. What you wrote down there.
Yeah, I'm just applying this construction recursively.
Right.
Right. I'm just applying this. So now that I have this, I can go in here and do that with the second variable.
Right.
And so on and so forth. All right. Any questions about that? So another way to think about this is, it's kind of like saying that for every possible entry in the truth table, there's a path that goes down the tree. Right? That's another way of putting it. Like if x is equal to 1, then it kind of goes down there. Then if x1 is equal to 1, it goes down here. And then if x2 is equal to 1, then it goes down another path or another path, so on and so forth. So essentially you have this tree and you have 2 to the n paths that go down. And so you have one entry for each path, which is a very believable construction. Like indeed, it actually gives you a formula, like not just a circuit. You actually get a formula. Okay. So that's done. So now we've argued that there is actually a circuit of size 50 times 2 to the n that computes f. How are we going to beat this bound? And so now we need to do a very clever construction. So let's think of this construction, but we don't want to go all the way to the end. So here's how we're going to think about it. I'm going to draw, this is x, the input, which is x1 to xn. So I'm going to think of the initial n minus k bits and the last k bits. And k is going to be really small here. K is going to be really small. I'm going to refer to this part as x less than n minus k. So I think of my input x as x less than n minus k, and then the last k bits. And then the last k bits, sorry. And that would be, x n minus k plus 1, x n minus k plus 2, up to xn k bits. So if we fix x less than n minus k to, say, z. So imagine that you fix this to z. So now we could look at f, z, but this is fixed. So they don't think of this as an input. And then you have x n minus k plus 1 up to xn, and that's k bits. If we fix z, we get a function of the form fz. I'll call this fz, 0, 1 to the k to 0, 1. We get a function of this form. So here is the clever bit now. Because we can now, let's go back to the 2 to the n construction. Here, we didn't really reuse any of the computation that we've done. And the whole point of a circuit was that you can actually reuse things that have been computed. So what Shannon's proof says is, well, let's try to reuse these fz's. So think of f as a collection of fz's. Collection of 2 to the n minus k fz's. So there are 2 to the n minus k's settings for z. For each setting of z, you end up with a k-bit function. Some of these k-bit functions may be repeated, in which case you don't have to compute them using separate circuits. So there are 2 to the 2 to the k possible FZs. Suppose we sort of pre-compute all of them using a separate circuit. So the way to think of this is you want to build a circuit for F. You don't know what F is. You're going to evaluate the truth table. You're going to look through the truth table and kind of figure out what the circuit should be. But before you do that, and so that would be, so just sorry to go back, this would be an inductive construction. You look at the truth table, you could say I break it up this way, then I break it up further and further down. So it's like I'm taking the truth table, I break it up into 2 parts, then I focus on each part separately. This approach is going to be different. It's going to say, well, hold on a bit. Let's break the input into the first n minus k bits and the last k bits. Now there are 2 to the 2 to the k possible functions on k bits. Let's just construct a circuit for each of them. So for each possible FZ, we'll go ahead and construct a circuit. This is a circuit for each possible f of z. Okay, this is a circuit for each possible f of z. Then you can think of what's going to happen is we use this construction above, the inductive construction, to just go and pick which fz we need. We're going to go and pick which fz we need. And every time we pick, we don't have to go and recompute that entire fz. We can just use whatever is there. And every possible fz, how much is it? There are 2 to the 2 to the k circuits times the circuit size for each of them to build this using the previous claim times 50 times 2 to the k, right? So the size of all of this is 50 times 2 to the power 2 to the k plus k. We apply this construction for the first n minus k bits. For the first n minus k bits, we apply this construction. So maybe the way to think of this is I'm just looking at the truth table. Okay. Minus k and k. So let's pick a particular setting for the n minus k bits. Let's take the all zeros. All zeros. Okay, and this is going to give you something of size 2 to the k here. And this is going to be some truth table. Now let's look at a different setting. Let's look at 0, 1, and then all zeros. 0, 1, all zeros, so on and so forth. And this is going to give me a separate truth table here. Now, if these 2 truth tables were the same, they could just go and link up to the same circuit. So this is going to be one of these. The second one is going to be one of these. The third one is going to be one of these, so on and so forth. But whatever function, whatever truth table you have over here is just one of these truth tables, or one of the truth tables induced by those circuits. So what this means is you only have to then apply the previous claim construction for n minus k bits, not for all the n bits. So here we were doing this for all the n bits. And over here we only do it for n minus k bits, after which we just go and link up with the right circuit. We can add an extra gate and then just connect to that. Like imagine adding a no-op gate and then just connecting to that output. Does this make sense? I'm going to write out the math, and then you need to work out the rest of the math. So what another way to think of it is we construct a multiplexer. We decide, using the first n minus k bits, we decide which function we want to use, which circuit we want to use. So the benefit of this approach is that you get to reuse the values constructed by these circuits, because some of these might be the same. Right? There are 2 to the n minus k of these. 2 to the n minus k such blocks. The number of values in each block, the total number of possible truth tables for each block is only 2 to the 2 to the k. So if k is really small, there are going to be many, many more blocks than there are possible truth tables, in which case we get to reuse values. So we follow previous claim construction for n minus k bits, and then use, I'll call the FZ circuits. The total size is at most, so we have the size of the earlier part is going to be 50 times 2 to the n minus k plus, we'll get from here 50 times 2 to the 2 to the k plus k. So I'm just going to ignore the 50 here, and I'll say this is equal up to a big O is 2 to the n divided by 2 to the k. So the point is you get to divide by 2 to the k over here, but then you have to pay a 2 to the 2 to the k plus k over here, and so now you optimize for the choice of k. Now you optimize for k to minimize this. So you can do this using calculus. You can do this using calculus, or you can actually just try to sort of look at, I'll show you how we'll do the optimization in a quicker way, and I want you to then fill in the rest of the details. If you do the optimization, then you basically get 2 to the n divided by n. Questions? And please ask, because this is a homework problem, so ask me any questions that you have about this.
This is a counting argument, right? So, in the end, we're proving that the number of functions that is greater, or okay.
No. So I'm sorry to interrupt.
That size, right?
So no, sorry to interrupt. This is not a counting argument. I'm explicitly constructing a circuit for you.
Oh, okay.
This is not a counting argument. Just like this construction is not a counting argument. It's actually constructing a circuit through induction.
But didn't we say at the start that we would be doing a counting argument?
The counting argument was only to prove that there exists a function that requires a circuit of size 2 to the n divided by n.
Okay.
That was the first part. That was where we counted the number of circuits of size s, and we counted the number of functions, with n inputs, and we showed one is greater than the other.
Okay.
In the second part, we actually have to construct a circuit for every function.
Okay.
Right, so we have to construct the circuit, and indeed I first showed you a simple construction, and now I'm showing you a more complex construction.
Yeah, I think I may have to just maybe think about it a little bit to fully internalize it. Yeah.
So okay, so maybe okay, so think of it the following way, right? This is the way I think the best way to understand this is look at the truth table, but just rearrange the truth table so that all things that are the same in the first n minus k, like imagine sorting it by sort of what's there in the first n minus k bits, right? So just sort the entire truth table. So you have these blocks. In each block, the first n minus k bits are the same. Right? So in each block, n minus k bits are the same. And so here you have all possible 2 to the k values of the remaining k bits. This is looking at all possible inputs. And then you could look at the truth table you get out of there. So this is just some vector of length 2 to the k. Like just some list or string of length 2 to the k. So once you fix the first n minus k bits, you get something of length 2 to the k, which is just the truth table of that restriction, as they call it. Okay, so far so good?
Yep.
Now, how many possible values of the truth table can there be? Well, only 2 to the 2 to the k. Right? So there are 2 to the 2 to the k possible values of this truth table. How many truth table chunks do you have? You have 2 to the n minus k. Now suppose this was much bigger than this, which you would expect. K is really small. If 2 to the n minus k is much bigger than 2 to the 2 to the k, then many of these truth tables must be repeated. It's like pigeonhole, right? It's like the same truth table is appearing multiple times. Which means you don't have to compute it every single time. You compute it once and you just reuse the value. You compute this once. You can imagine like there is a circuit that computes this truth table chunk once. There's some circuit, and that goes and is used in multiple different places. The same truth table might be appearing so many times that you don't have to redo the computation of that truth table, which is you're computing this truth table chunk by a circuit. So in the previous construction, you were just doing an independent construction for each of these chunks. But now what you're observing is you're being a little careful. Like you can also think of it like dynamic programming. Once you store the solutions for the sub-problems, you reuse them. In the previous construction, you were like recomputing them with a separate circuit. And here you're reusing them. But you have to be careful. You have to choose the k carefully so that you get a benefit. So here's the trade-off. The smaller the k is, the more repeats there are, the cheaper it is to build the circuit for every k. If k is small, then all of this building is small. But then the gains you get are also small. Because you have to do the standard computation up to n minus k.
So on the homework, I don't remember the exact question. Are we just formalizing this essentially?
You're going to formalize this and you're going to complete the proof. The proof is not yet done, right? So you need to choose a k. Yeah, you just have to formalize this argument. And I'm just going to write out the last part. So now choose K so that the size is O of 2 to the n divided by n. And that's basically your homework. You have to do that and sort of then like just write all of this stuff down. And that would end the proof. So what is remarkable about this theorem, what is remarkable about the fact that you can actually choose a K so that it completely matches the lower bound that we got. Like we're able, like, and you know what's even more, I guess, even more remarkable is you can even get the constant to be down exactly. Although this argument doesn't deal with constants well enough. We can pause for a couple minutes here, because after this I'm going to kind of move on to the next topic. My main point for today was to show Shannon's theorem. So let's pause here. You can ask me any questions that you have, and then we'll come back to we'll go on from here. So now with the proof of Shannon's theorem, let's now, so far we've been talking about circuits, let's go back to talking about languages, as we've done so far. So I'm going to define something called a circuit family, not just a circuit. So a circuit family is a collection of circuits C of n for each n and n, I should say, for each n and n. It's a collection where C of n, C of n has n input bits. Right, so this now can decide a language, a family of circuits, and we'll say a circuit family C computes, or you can even say decides, language L if L is equal to the set X, so that C of X is equal to 1, where X has length n. Right? So it just says that a circuit family computes or decides a language if essentially the language is exactly the set of strings that that circuit family kind of accepts. Right? You could think of the output being accept or reject being a 1 or a 0. Okay? And furthermore, we'll say that L, okay, so a circuit family C has size S of n, has a size as a function if for all n, and I'll just say that the size of C of n is is O of S of n. Right? These are the basic definitions. And so we just proved a theorem which is for all languages, and really it's all languages L. L is computed by a circuit family of size 2 to the n divided by n. All languages, even if L is undecidable. Even undecidable. Every language is computed by some circuit family. So why isn't there a contradiction? Why, we talked about the existence of uncomputable languages. So then how can every language be computed by a circuit family? There isn't a contradiction, but do you see the point? So what is the response to that? What is the size of the representation of a circuit family? Like how much can you write down the description of a circuit family? Is my question clear? Like how do you write down a circuit? Like you say, okay, here's my circuit of a particular size. Okay, but that doesn't tell you what the circuit of the next size is. So then you say, okay, I'm going to write down the circuit of that size. That doesn't tell you what the circuit of the next size is. So write down that size. So if you think about it, the description of a circuit family C is potentially infinite. An algorithm or a Turing machine always has a finite description. And that's why you have undecidability, because the description of functions are infinitely long strings, and the description of an algorithm or Turing machine is a finite length string, and then you have diagonalization and countability and uncountability. But circuit families, the description is infinite. Therefore, in some sense, there are uncountably many circuit families, but there are countably many algorithms. It's a very important point. The very important point.
So it's not that the individual circuits are infinite. It's that the family of every circuit in the family, the description of that is infinite potentially.
Exactly. So think of it this way: that an algorithm tells you how to deal with inputs of any possible size. A circuit only tells you how to deal with inputs of a fixed size.
Right.
So you have to now describe how to deal with inputs of all possible sizes, which is now going to lead to an infinite description.
Oh. Huh.
Right? It's a very important point here.
So what did we say separates one circuit family from a different circuit family? Is it strictly it's not strictly the size of the input.
No, so think of it as a circuit family. Okay, so here's another way of describing it. When you write a piece of code, or at least in general, you think of the code or the Turing machine as having the ability to deal with inputs of all possible size. So you have a finite set of instructions to deal with all possible sizes of inputs. With a circuit, you actually get to specify a different program for every possible size. So it's not a finite description. You're actually giving an infinite description. I mean, by giving, you see what I'm saying, right? There's basically, there's no, a circuit family does not necessarily have a finite description. And that's why it's able to compute undecidable languages, because in some sense we can't really construct circuit families because we need to do finite constructions.
I see what you're saying now.
And we will revisit this topic. So you might say, okay, what does it mean? Then I can't even use a circuit family to compute, because how do I give a finite description? Then we can talk about circuit families that have finite descriptions. And then we will bring Turing machines back into the picture when we talk about that. But what is important is to really get this point, that the circuit viewpoint is fundamentally different from an algorithmic viewpoint because of this condition here. That doesn't mean that circuits are not worth studying, and actually they're fascinating mathematically, and we'll see interesting things about them. But the description of a circuit family is potentially infinite, and an algorithm or Turing machine has a finite description. The technical term used for this is what's called non-uniformity. What non-uniformity means is basically a potentially infinite description, or another way to think of it as a different algorithm for every n, where this is the input size. And this is a non-uniform, what's referred to as a non-uniform model of computation. Model of computation. When there are others other than circuits. There are also things called decision trees, and there are various sort of other models. And a uniform model of computation. This is always a finite description. So this is like a Turing machine or an algorithm. Okay? So that's why obviously we don't have any such statement, but the fact that we have such statements about circuits now starts saying, actually, it's nicer to think about circuits in some ways, because we can actually say that all languages can be computed by a circuit family of an explicit size. We can actually even write down the size. Like, we can't say something like all languages are computable by Turing machines that run in a particular time. But we can actually say that all languages can be computed by circuit families of a particular size. So this measure of complexity, this is the circuit complexity of the language, is in many ways a nicer quantity to deal with than the time complexity, which is like the best running time. Because running times can just become bigger and bigger and bigger. Maybe there's a language that needs, doubly exponential runtime or doubly exponential space. But with the circuit size, it's at most 2 to the n divided by n for any language. And that's one of the reasons why complexity theorists who were trying to understand computational complexity then started bringing in circuit complexity into the viewpoint, saying this is an easier viewpoint. Can we start relating this to things like running time and space? And we'll be seeing that in the next, probably in the next couple of lectures. But I want to sort of make sure that this point is clear. This is a uniform model of computation. That's a finite description. non-uniformity is a potentially infinite description, and circuit families are non-uniform. It's a non-uniform model of computation. It's a method of computation where the descriptions are themselves infinite. So now let me give a definition. Just as we talked about time and space, we're now going to define something called size S of n is the family of languages computed by S of n sized circuit families. And this is also called, this is where it comes to circuit complexity. We talked about time complexity and space complexity as resources that are needed to compute or decide a particular language. Now we can talk about the circuit complexity, which is the circuit size required to compute a particular language. And what is nice is that sort of all languages lie in size 2 to the n divided by n. And now we can start asking, what can be computed by circuits that are smaller? And this brings the next complexity class of interest, which is called p/poly, which is all functions computable by polynomial sized circuits. This is all languages computable by polynomial sized circuits. So if L is in p/poly, we can construct efficient circuits to decide L. It doesn't give an algorithm. It doesn't give an efficient algorithm, but it says that there exists an efficient family, which is really a small circuit family. Okay, and I want to add. Okay. And just as we have hierarchy theorems, we have something that's called the non-uniform hierarchy theorem. So I'll state it. I won't give the proof. I'll just sort of mention how it's proved. But you will need the non-uniform hierarchy theorem. It's important that you understand it. You may need it in the homework, and you may need it for some of the exam questions. So let n be less than S of n, be 2 to the n divided by n. This is just some sort of function. Then size S of n is a strict subset of size 4 times S of n. Sorry, this should be 4 times S of n. So the idea is that when you have larger circuits, you can compute more functions. Just as we had, remember, we had this other the time hierarchy theorem that says, d time of of T of n was a strict subset of D time of T prime n when T prime n is greater than Tn log Tn, because you needed the efficient simulation theorem. That was the hierarchy theorem for running time. There's a hierarchy theorem for size, and this is actually an easy consequence of Shannon's theorem. Essentially what you can do is for every size you can find some function that cannot be computed in that size, but it can be computed in some larger size, and then that gives the non-uniform hierarchy theorem. Okay, so this is the non-uniform hierarchy theorem. This is an important fact. And there is the definition of P/poly, which is all languages computable by polynomial sized circuits. And the goal for the next lecture is to investigate the relationship between P/poly and NP, and also to understand the relationship of P/poly with P. So I say it's not obvious that P, which is polynomial time, is contained in P/poly. It seems to be completely different. P/poly is size of a circuit, and P, as we define it, is with running time. But we'll actually show that P is contained in P/poly, and so we'll use like a Cook-Levin style construction. And once we have, and that's a very important tool that will help us understand even things within P. So I'll end here. I'll take any questions that you have, and when we come for our next lecture, we will continue with circuit complexity.